Hey there, ladies and gentlemen. Welcome to the Burma Nation. We are talking, I think my face is in the way here, so we're going to move it for you so you can see it. But we are talking today about lesson 8.5. We're talking, or get the beginnings of talking about factoring. And this is using the distributive property. So what factoring is when we take a product of prime numbers and variables, no variables has an exponent that is greater than 1. That's the math lingo. Factoring is when we undo the math that's going on. If you recall back in earlier years, we factored out numbers and you'd write down a list of the prime factors, and this is going to be kind of similar to that. So we're going to have our expanded form in a more algebraic type of a way. All right, so I have, let's go red. I like red. We're going to break this down. If you remember a factor tree, you would break down the number 18 into two numbers that multiply to make 18, and then you would circle things that are prime. 2 is prime because it can't be broken down any further. And then two numbers that multiply to make 9 are 3 and 3, and numbers that are prime get circled. So then to start this off, I have 2 times 3 times 3 for me trying to factor things out. Now these variables over here, we're just going to break them down as well. So if you have x to the second power, that gets factored out into having two x's, or an x times an x. And then y to the third power is 3 of them. So we're going to have y times y times y times y. And what you're going to do is you're going to write numbers in order from least to greatest of their primes, and then you're going to have them alphabetical with the variables. And that's how we make things factored out completely. So this would be my completely factored version of 18x to the second power, y to the third power. So maybe you want to hit pause, try this one on your own and see what it looks like. So we do 15a to the third power, b to the second. You're going to break down 15 into its prime numbers. So that's a 3 and a 5. And you can't break either of those down further, so it just becomes 3 times 5. So my answer so far has a 3 and a times 5. And then I'm going to have a to the third power breaks down into times a, times a, times a, because there's 3 of them. And then times b to the second power, or times 2 b's, times b times b. And then this, if we were to do all that math, turns back into that number. So we're undoing the math. So this is going to be the theme for this part of Chapter 8, this part of the year, is we're going to start undoing the things that we worked on doing the entire year so far. So it's going to be kind of weird, and that's what factoring is. So part of factoring is coming up with greatest common factors. Again, you should recognize those terms. So what we're going to do is we're going to find the largest thing that we can divide out of both of these numbers that's in common. So if you look at the number 27 and you look at the number 15, the largest actual number that you can divide out of a 15 and a 27 would be what? Think to yourself. Please say 3. So the largest number I can divide out of both of them is a 3. And the largest number of A's I can take from both of them is just one of the A's. And the largest number of B's I can take from both of them is just one of the B's. Now because they both don't have a C, then the C just stays put. So we divided out of 27 a 3AB. We divided out of this 15AB to the second C. We divided out a 3AB. The GCF is 3AB. Now the cool thing is the leftover stuff that we took out. So if I take out and divide out a 3, I'm left with a 9. If I divide out an A, I'm left with an A. If I take out a B, I'm left with just nothing else because there's no more B's left. So if I multiply these two numbers together, I should get what we had at the beginning. So we're undoing stuff. Now you can imagine that if I had another one here, if I multiplied or divided out a 3 from this 15, I'd be left over with a 5. If I divided out an A, I don't have any more A's left. I divided out one of the B's, so I do have a B left, because B to the second divided by a B makes one B left. And I didn't divide out any C's, so the C is still there. So if I multiplied this number times this number, we would end up with that 15ab to the second c. And that's the whole goal here, folks, is we're going to start recognizing the things that we take out and then what's left over to help us solve more complicated problems. So on example 2 here, maybe you want to go ahead and try to do this one without me first, and then see if you can do it with me here or get the same answer. So here we are, 39 and 26. The largest number I can take out of both of them is a 13. The largest number of x's I can divide out of both of them is just 1x, or x to the first power. The largest number of y's I can take out of both of them would be y to the third power. So my GCF, which we're trying to find, is 13x y to the third. Now if you wanted to go a little bit further, you could take my leftover stuff would then be a 3x for the first one, and the second one would be left over with a 2y. So when I multiply these things to that, we should get the original numbers that we started with. All right, and make sure that you understand this. It says find the GCF. This is the answer. Okay, we don't need to do this stuff yet when it says find the GCF. So make sure you understand the difference. This is the leftover stuff. We'll be using that more so in different types of problems. All right, so we have a real world application. The lengths of the sides of a triangle are 12yz to the second, 8wz. Did I say y? I meant w. And then 16w to the second z. We're supposed to find the GCF of the three lengths. So you're finding the largest thing you can divide out of all three of these numbers. We don't care what's left over. We're just trying to find the largest thing that we can divide out of all three of them. So if you look at 12, 8, and 16, the largest number we can take out is a 4. The largest number of w's we can take out is just 1w, or w to the first. And then the largest number of z's we can take out is just one of the z's. So then that is my GCF, and I'm done. Beautiful. All right, let's make things a little bit harder. There's something called the zero product property. And we learned about this earlier. What it means is that if I have a number or two numbers, like maybe x times y equals to 0, what it means is that one or both of these numbers has to be 0 for the answer to be 0. So what we do in situations like in example A is we take and we set both of them to be equal to 0. So this is the most basic type of a problem. Because we have two numbers that are multiplied together and the answer is 0, that means that x minus 2 could be the one that equals 0, or it could mean that 4x minus 1 is the one that equals 0. So what we do is we solve both of these individual equations and get our two possible answers. So we have a plus 2 to both sides to find out that x is equal to a 2, or we do the plus 1, and then divide by 4 to get x could also be equal to 1/4. So these are our two possible answers. These are called the roots of the solution for us. They're going to end up making what's called a parabola. So this is the x-axis. The roots are where it crosses the x-axis. So these dots right here are what we're finding when we solve problems like this. This last one, example B. We will do that one when we get into class tomorrow. And just try to see if you can solve that one. We'll see what kind of skills you guys have. I'll get you started. And again, this is just for you to challenge yourself a little bit. We want this to be equal to 0. So I'm going to bring that 4y over to the other side, and it's going to say 12y squared minus 4y is equal to 0. And what I want you to do is see if you can figure out, by using our GCF stuff, if you can figure out how to make this work. So our goal is to get down to two things here that multiply together to equal to 0. So see if you can pull something out here, and we will go over this first thing when you get to class tomorrow. All right, folks, this is the Berma Nation, and I'm signing off. Have a great one.